Hi, I'm Ryan, and I'm going to be teaching you MENG2018 Applied Mechanics this semester. We're going to get started on Simple Machines, which is chapter number 7 in your 3A1 textbook. And the portion we're going to cover is about the first half of chapter 7. How it's going to work in this course is we're going to have some pre-recorded lectures, so similar to what you'll see today. In it, usually what I do is work through a worksheet, and you can download the worksheet off of Blackboard if you want to print one out and have your own copy. Otherwise, you can follow through the lecture itself. And for the most part, most of my material follows what's on your 3A1 textbook chapters. So you also have those resources that you could use to follow through. Each week you're going to have an assignment or a lab, so we'll have some sort of work that you need to produce for me. And then as well, we also have 1 hour that's assigned to us as a synchronous portion. So it's 1 hour where I'll be available via video conference, and we can work through problems together. Usually I approach those as a drop-in session, so sometimes we may have 20 students, sometimes we may have 5 students. Come if you need the help and you need to do some practice questions with us and you find it valuable. Okay, so let's get started on our content. Okay, so as I said, if you need the exercise sheet, you could download it off of Blackboard. So simple machines, we have a number of simple machines that exist. For instance, over here we've got a person using a lever to try and move a heavy load. And so we have lots of different simple machines. Lever would be a classic simple machine. A screw or an inclined plane, pulley. So we have a whole bunch of different simple machines. And if we think about what a simple machine does, a simple machine, often what a student might say or somebody might say is that it makes work easier. Okay, so it makes work easier. Okay, and it's not 100% true, that definition. It may seem like makes work easier, but basically what's happening is we're having a trade-off. Okay, we're doing the same amount of work, but instead of having a reduction of work, what we're doing is we're trading off the force that we need to apply for some extra distance. Okay, so a simple machine, really what it's doing is it's trading off forces for distance. So we have to do less force over a greater distance. When we talk about simple machines, we talk about a couple of terms. So first one we talk about would be mechanical advantage. And what mechanical advantage is a measure of the forces in the machine. So when we have a mechanical advantage, what we have is a ratio of a force compared to a force. Okay. And if we come back to our guy using our lever, what we might have would be the force that we might consider to be the load. And we have the effort that the person puts. So he may be pushing down, and we may have an effort. Okay. In the result, his effort is going to be transmitted through the machine, and we may be able to push up to move that load. Okay, so we have an effort and a load. When we talk about mechanical advantage, we have a ratio of forces. Mechanical advantage is always going to be larger than 1. So what that means is that I need to have my larger force on the top. And if I look at my man trying to use that lever, well, the larger force is going to be the force of the load. So force of the load compared to the force of the effort. And so what I have is a ratio. And as I said, mechanical advantage is always going to be above 1. And it's a measure really of the amplification or the multiplication of the forces in my machine. We also have another term, which is the velocity ratio. And when we talked about the work that's done, or the how does a simple machine work for us, we said it was work was easier, and we talked about the force being changed, or we sacrifice force for distance. And so velocity ratio is the ratio dealing with the distances. So distance. And so once again, velocity ratio is going to be larger than 1. We're going to have a ratio of the distance that my load moves compared to my effort. In this case, it's going to be the distance that the effort moves, because it has to move a larger distance compared to the distance that the load moves. Okay. Within your academic supplement, you have a section on lifting machines, and here's what you've got. So you have your MA, your mechanical advantage, which is a measure of your load per effort, and in this case they're talking about the forces. And then as well you have your velocity ratio, which is the distance that the effort moves compared to the distance that the load moves. Okay, so we're always going to remember those couple terms, and they're going to come up in a lot of questions in this section. Okay, so just a couple of practice questions relating to those terms. So how much load can be moved by a simple machine if an effort of 200 newtons is applied and the machine has a mechanical advantage of 8.3? Okay, so our definition of mechanical advantage is equal to ratio of forces. The force of the load is going to be larger than the force of the effort. Okay, and that gets us our equation. We're going to be solving for force of the load here, which means that we need to rearrange this equation. Okay, it's assumed that you are knowledgeable on rearranging equations. However, if you are having some struggles, please reach out to me, because it's a skill that you definitely need to have and need to work away at with this course. Okay. However, if we're going to rearrange this equation, so what will end up happening is essentially we'll multiply both sides by the force of the effort, which will bring that guy up to that side. So what we would be left with is force of my effort times the mechanical advantage is going to be equal to my force of my load. I'm going to substitute in some values. So force of my effort is 200 newtons times the mechanical advantage 8.3 is going to be equal to the force of the load. Okay, just a couple things to point out unit-wise. Mechanical advantage has no units to it, so it's just a number, it's just a ratio. So we don't have any units assigned to mechanical advantage. However, we do have a unit to our force, newtons, and that will lead to having a answer of newtons in our final answer for our load. So 200 times 8.3 gives us 1,660 newtons is equal to the force of the load. Okay. We have example 3. So in a simple machine, an effort of 300 newtons is applied over a distance of 4 meters to move a load 50 centimeters. And what is the velocity ratio for this operation? So my velocity ratio is equal to distance compared to distance. The distance that my effort moves is larger, so it's on top, compared to the distance that my load moves. In this case, what I have is a distance of 4, and it's going to move the load of 50 centimeters. Okay, so my effort is going to be 4 meters, and my load is going to be 50 centimeters. Okay. I have a problem with my units. They need to be compatible. All right, so 50 centimeters, 4 meters. I'm not going to end up with units that cancel out. Okay, so what I'd like to do is be a little bit more considerate with my units. So 50 centimeters, and if we recall how to convert, times 1 meter per 100 centimeters is going to be equal to 0.5 meters. So is equal to 4 meters divided by 0.5 meters, and I end up with a velocity ratio of 8. We'll note that the effort 300 newtons wasn't required in the problem. It was just some extra information for us. Okay. We use the term work, so we said simple machines make work easier. Okay, and so let's explore a little bit about work. First of all, when we talk about work in mechanics, what we say, it's a force times a distance. So work is equal to a force times a distance. Okay, so let's see if we can figure out what efficiency is in terms of work. So when we talk about efficiency, we also have the idea that efficiency is really what do we get out compared to what did we put in. So if we talk about efficiency in terms of work, what we might say is our efficiency is equal to work out compared to work in. And if we talk about a simple machine, the work out is the work that goes to moving the load, and the work in is the work we put into the effort. Since work is a force times a distance, it's going to be equal to a force on the load times the distance that the load moves compared to the force that is applied through the effort times the distance that the effort moves. Okay, and so this is kind of interesting if we get to this point, because we've already come up with a few ratios. We had mechanical advantage, which was the force that of the load compared to the force of the effort. And we had VR, which was the distance that the effort moves compared to the distance that the load moves. And if we look, we have this ratio here, FL over FE, and we have this ratio, although it's upside down, right here. Okay. What the net result of all this is that this guy is equal to this, which was MA, the FL over FE, divided by MA, divide it by VR. So we have this equation which says the efficiency, by the way, I've used this Greek symbol for efficiency, is going to be the ratio of the mechanical advantage compared to the VR. Okay. So efficiency in terms of VR and MA, efficiency is MA upon VR. And we have that still, so that guy is given to us in our academic supplement. So the efficiency of a simple machine is MA divided by VR, and you've got that symbol there equivalent to efficiency. A system that is 100% efficient is going to have a case where our efficiency is 100%, or as a decimal, 1 is going to be equal to MA upon VR. And in this case, MA is equal to VR if we have a 100% efficient machine. If we don't have a 100% efficient machine, then we have a case where we have differences between MA and VR. And MA is always going to be less than VR. And we can think about that where, again, we had MA that was based on the forces, and we had VR which was based on the distances. Oops. Well, the distances are never going to change. Your geometry of your machine is never going to change. So VR is always set. However, if a system is inefficient, so it has friction or other losses, it's going to mean that we're going to have a larger force required, or else, in other words, we're going to have a smaller MA. Okay. If we have a term for mechanical advantage when it's 100% efficient, and if we do have that, sometimes you may see this in a question, but it would be the ideal MA means that it's 100% efficient. Okay, so let's look at one more question. Okay, so we have a simple machine and it lifts a load of 1,500 newtons and it lifts it a distance of 5 meters. The actual effort applied is 125 newtons. What is the MA of the machine? How far must the effort move if the machine is 75% efficient? So this is a pretty common style of question at your third class level. You're going to need to be able to deal with MA, VR, and efficiency to find an unknown quantity. So what I'd suggest is that a good starting point for a question like this is to just make note of what we know and arrange the units so that they're compatible. So move all of the forces into newtons, all of the distances into meters or centimeters. As long as they're consistent, you'll be okay in these questions. So I know that I'm going to need to know the force for the load, the force for the effort. I'm going to need to know the distance for the load, and I'm going to need to know the distance for the effort. I'm going to need to know efficiency, MA, VR, I may need to know. So I got a whole bunch of stuff just to take note of. So as I go through the question, so lifts a load of 1,500 newtons, so that's my force of my load. Distance of the load of 5 meters. The actual effort applied is 125 newtons. So those units are compatible with the forces, so that's good. What is the MA of the machine? So I'll make note that that's what I'm being asked. And how far must the effort move? So I'm going to be asked that guy. if the machine is 75% efficient. So 75% efficiency, and I'm always going to want to use efficiency as a decimal in these questions, so 0.75 would be what I'd use for my efficiency. Okay, so where do we start? Well, I know that I have my two forces, and I can use that to find my MA. So MA is going to be my force of my load compared to the force of my effort. (1,500 newtons divided by 125 newtons, and that's going to equal 12. No units for MA, so newtons and newtons cancels out. Once I've found MA, then what I can do is use my efficiency to find VR. So efficiency is equal to MA divided by VR. I'll rearrange to solve for VR. So VR is going to come up to the top and efficiency is going to come down. So what I'll be left with is, when I rearrange that, VR is equal to MA upon efficiency. So is equal to 12 divided by 0.75, and that equals 16. Last thing that I'm going to do is I'm going to find my distance for my effort, and I use VR to find that. So VR is going to be the distance for my effort compared to the distance of my load. I'm going to rearrange this guy, so solving for distance of effort, which means my distance of my load is going to come up to the top. So my distance of my effort is equal to VR times my distance of my load, equal to 16 times 5.0 meters, and my distance of my effort is 80 meters. Okay, so I think I've got my answers. VR of 80, my distance of my effort of 80, and my MA of 12.